Hey all, it's been a long time, but since you all are here, let's directly jump into the topic. Recently, there has been a lot of buzzword around Agentic AI and conversational AI, so I thought let's cover that into my list now. So, Agentic AI began with the popularization of ML and especially in the terms of large language models that are LLMs. So, we'll be covering those into a great detail. The prerequisite for this playlist will be some terms of vectors and matrices because we'll be covering some foundational papers that might need the knowledge and concept of rank, matrix multiplication, and pretty basic stuffs of related with tensors. Also, it would be preferred if we have something around mean expectation, variance, covariance, such statistical terms, but yeah, they're not that much required. So yeah, let's begin with the playlist and let's see what all things we'll be covering into it. So let's go through the playlist once. So first we'll be covering LSTMs. LSTMs we won't be covering into much depth because nothing much interesting is going around these days. Plus it's outdated, but it is what it is at the core of transformer. So we need it to understand what it is doing at the core. We'll describe a simple architecture of LSTM. We'll understand how the loss is calculated and why it is called backpropagation through time. We'll understand the pros and cons. Pros and cons is already covered, so not much depth into it. And then we'll create an LSTM in PyTorch, we'll train it, and then we'll see the inferencing and how it works. The second topic we'll be doing is transformers. In transformers, we have already covered attention and then its architecture, and then using attention model to code transformer from scratch. So we won't be doing that. The second important thing is embedding. So as we have already discussed that language models or any of the ML models, they don't understand text, they understand numerical data. So, I mean, vectors. So how is that sentence used to train an ML? Because we need some method to convert this particular sentence into its representation into vectors such that the essence of this sentence is not lost. So that is covered through embeddings. We'll go through deep dive into embeddings. Then we'll go through way forward. Way forward is like how transformer models are now used in different aspects like vision transformer. Then we have the concept of deformed attention. So we'll try to cover a paper around it, probably deformed attention. So that's what we'll be doing into transformer section. The third one is Model Zoo. Model Zoo is like we currently experience a lot of ML models around LLMs, such as there we have GPT multi models, then we have thinking models, then we have Gemini models, then we have Cloud. So there are tons of models around there. So we'll just take a look over them and then we just try to differentiate it on different benchmarks, like which model to use and when to use. So these are all pretty much static stuffs. And then we'll start with training LLMs. This is the most important part of this playlist. So for any large language models, we need a large amount of data. So that's how they got their name, large language models. So for data preparation, we have certain training objectives, like what is the objective that you are trying to train your LLM on. So we'll take a look over them, the CLM, MLM, DLM, and RLHF, out of which RLHF is more important. So we'll try to discuss a paper around it. CLM stand for casual language modeling, then MLM is, I think, masked language modeling, and PLM is pre-trained language modeling, and RLHF is reinforcement learning from human feedback. Then the second most important thing is fine tuning because this is what is currently happening into the industries. Like nobody's going to train a full fine tuned model, and nobody's going to train a full large scale LLM from the scratch on your data because first of all we don't have that much data for our specific use case, and second one, it is computer intensive. So we have certain techniques of fine tuning it. Fine tuning basically means taking an existing LLM with all its parameters and then modifying those parameters in such a way that it fits our need. For example, if you have some customer around real estate, so your LLM should be able to understand the queries specific to the real estate. So that is what fine tuning means. We'll understand two techniques around it. One is adapter and one is PEFT. PEFT basically represent performance efficient fine tuning. Then full skill training, I might cover it into from just overview because I don't have that much of compute resource to train it. But yeah, we'll just go through it. And then evaluation of LLMs. So we'll discuss certain benchmarks around certain type of data and what does it means to evaluate LLMs and how it is done. So that's something we'll be covering over here. The current state of the art are the reasoning models. So we'll be covering reasoning models in lot details because that is how your AI agent can become more efficient and more accurate to your particular query, especially if the query is a bit complex. So we'll go through the reasoning. It started in 1970s around, so that's not pretty new, but yeah, that's something will be needed. So COT decoding, COT stand for chain of thought. So if you have heard about Rapid Bansal into Meta's AI lab, so he is the one who revolutionized LLMs by introducing chain of thoughts. So we'll be going through chain of thought decodings and certain prompting methods. TOT is basically train of thoughts, an advanced version of COT, and certain prompting that that can help you train, and then that can help you not train, but that can help you in your model bit well. We'll be covering those stuff, and then we'll be going through RL fine tuning. So these are pretty much statics, which in which we'll be spending most of our time on, and then the finally our last thing will be to build an AI agent. So this is not an complete exhaustive list, but yeah, it can change accordingly. But this is what I've thought of covering. So let's just quickly go through the LSTM concepts. We won't be diving into much depth into it because it's not used anymore after the arrival of transformers and all, because first transformer provide you parallel training. LSTMs are mostly sequential, and they still suffer from context loss. So let's just go through it. So dawn of neural networks, we all know that earlier we used to have limited resources and limited data, due to which the neural networks never saw that age of golden dawn. But since 2007 and 2005 onwards, they gained popularity due to high compute resources, which were having no GPUs and a vast amount of data. So we had an introduction with the classical ML, but will be mostly focused into language problems. Language problems employs the things where texts are involved. So text conversion into numerical data, and then we follow the embedding process and all. So the first type of language models were RNNs. These were pretty basics. They had the vanishing problem. So vanishing problem means if the context length, I mean, if the sentence goes a bit lengthy, the RNN forgot what it was earlier when it was trying to predict the next tokens. So let's just quickly go through a fundamental concepts of LLM, LSTMs, or whatever we are having. All of these are probabilistic model. This is the core concept of LLMs and LSTMs. So what is a probabilistic model? Probabilistic model is that they work on a probability theory. The probability theory is that what suppose if you have an LSTM and it is trying to predict a sentence. I mean, let's say language translation. For example, I am ML engineer and I want to translate it into Hindi. Translate into Hindi. So this is a sequence mapping statement. Sequence mapping means each words get mapped to a particular word into Hindi. So this is a sequence mapping problem. But for any kind of such problems, the LLM tries to predict the probability of a word. So what it does, when we are training, we have a certain words and it has, let's say, this is just an abstract view. So it has a certain access to data. Let's say this is the data of LLM, on which it was trained, and it just is a use corpus of data. So the I, am, he, she, and so many other words are there. So when it's trying to predict or to begin a sentence, what it does is find probability that which sentence will having the highest probability of coming it here, and that particular word it will pick it up from its bag of word and it will put it here. So let's say for example for the first word it was I. When it tried to predict this next token, what it does calculate is just revisiting the Bayes theorem. What it calculates is probability of second word given first word was I. So this is what we call as context. So this is what it trying to predict, and here it will come M. Now when it will try to predict the third word, the second thing that will come to its mind is probability of same thing, third word given previous words were I and M, or previous sentence was I am. So it will try to complete the probability of this. So I am the, or something like that. So this is the fundamental principle of working of LLMs, that it works on a probabilistic model. So this point will come into consideration when we'll be listening or when we'll be learning to chain of thoughts or train of thoughts. In chain of thoughts or train of thoughts, it was found that if you change the probability somehow of this bag of words, so that the starting space, I mean, let's call that the words which are coming up to this place, let's call it some space A. If this space get altered to some other vector space, let's say space B, the whole output of LLM will change. So this is how chain of thought. This was the principle of working of chain of thought, that if you give LLM simple steps rather than saying everything into once, a simple steps to think upon, it can better reason. And that was where the beginning of reasoning models come into picture, that provided step-by-step instructions to follow a complicated task. What they are doing, they are at that point of time, they are simply changing the space of the first word, and that lead to better result generation and better accuracy. So we'll discuss it into detail when we'll be working with chain of thoughts. So this was a simple RNN. RNN we won't be covering much. So just H is a hidden state. Hidden state is something, it is a hyperparameter which we provide, and it basically determines what will be the length of context that this LLM or RSTM will be able to capture. Sorry, not LLM, LSTM or RNN will be able to capture, and it is a time sequence model. So HT defined the hidden state at time t, and so on. Let's come to the LSTM. So RNN had vanishing gradient problem, and it doesn't have memory. I mean, very little. So not good for large sentences or sequence mapping problems. Then come into LSTMs. It has a memory cell. LSTM has a larger context, and it almost eliminated the problem of vanishing gradient, but it is still at to some extent it was there still. So what is happening over here is that this is a LSTM. We call it as an LSTM. Here you have a memory part, and here you have a hidden state. Hidden state is same as what it was RNN. The memory part come into picture. So memory part is something, consider it as a data for this cell. Data for this cell, and this hidden state is like context length. The higher the number of dimension into hidden state, the better it will be able to capture larger context. But again, if there is a larger context, the more the problem of finishing gradient you will be having. So this is a hyperparameter which we have to fix and tune. So what's happening inside a LSTM cell is just, I'm just giving an abstract idea. There is a lot of maths going on here. So we have three gates: forget gate, input gate, and output gate. Uh, Input gate we call it as selective write, and output gate we call it selective write. Now consider a real life example. So if you are fed up with huge amount of data, so consider this memory and data set, they constitute a large amount of data. So first thing what you'll try to see, you will try to see that what all things I can easily forget from here. I mean, what all things are not important for me to answer. So that come into forget get. So we calculate this is a matrix basically, uh, trainable parameter. So we calculate that by using forget get. So memory and data hidden state comes, some of the data gets dropped over here. Then comes the input gate. So input gate, whatever after this forget gate, whatever I mean from this particular memory and hidden state, these are directly passed into the input gate. So from this, only few kind of data will be required for me to actually process and give a valid result. So that is calculated by the input gate. Again, a trainable parameter, trainable matrix. Then then comes the output gate. So whatever data I have processed on the basis of the input, not all of that data will be relevant for the next cell. So that gets passed into output gate, and from there the data filtering is done. So these all gates are the important of LSTM, and these all gates are kind of, you can say, data filtering mechanism. Like they are metrics that are getting trained through backward propagation through time, and they are getting tuned so as to filter out irrelevant context from the data. And then for each of the LSTM cell, you will get a CT and an ST. CT different CT cells the what's the memory after processing for the timestamp t, and ST is again hidden state after passing through the LSTM cell at time t. So this is pretty much at about LSTM. Now we'll see how the code works into LSTM on PyTorch. Uh, we can also no, that's pretty much it. And then we'll simply see how the LSTM coding works into PyTorch, and then we'll just move on to the embeddings part. So, let's start exploring the code. So this is a pretty simple one. We have a torch module. We'll just simply import it out. And then we have this LSTM module. So LSTM module will have an LSTM cell, and then we'll have a forward layer. And then this is a number of layers. Number of layers define how many times you want this particular layer to go on. So this is again a hyperparameter. So in this hidden size will be hyperparameter. So this one, as we were discussing validation. So this is your hidden state. This is your hidden state, and this will be a hyperparameter to this. The longer the hidden state length, the more context it will be able to acclimate into it. But yeah, we'll be using a pretty small hidden state for this. And then what it will do, it will apply a forward layer, and then this is the forward layer that we have. This, this particular forward layer. So let's see. Let's just go through our data set. What it is. This is a pretty simple LST module. We have this data set over here. Let's just quickly go through it. Now I can just so here we have the data set, mean temperature, humidity, wind speed, and mean pressure. So we'll try to predict mean temperature. Mean temperature will be our y, and this humidity, wind pressure, and mean pressure will be our x. So if for a particular data point we have three input feature and one output feature. Let's quickly go through the dataset class. So here we'll have certain create sequence. So every dataset, every dataset base class have to import three things: init, length, and get item. Like these are the abstract classes that every class which is importing dataset needs to implement. So let's see how dataset preparation is done for LSTM. So let's say we are predicting temperature. We have let's say mm, wind speed, humidity, pressure, temperature. Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So for 1, 2, 3, the output is 4. For 5, 6, 7, the output is 8. For 9, 10, 11, the output is 12. For 13, 14, 15, the output is 16. So what it is basically it is like a context size. So if we just write it in a simpler form, so 1, 2, 3, 5, 6, 7, 9, 10, 11, and then 13, 14, 15. For this the output are 4, 8, 12, 16. So this is our input data. Now we have something called window length. So if we set window length to let's say 2. So what it will do, the code which we have written, it will take these two as a single thing and it will predict 12. Then for example, so our data set will become something like this: 1, 2, 3, 5, 6, 7. For this the prediction should be 12. The second will be 5, 6, 7, 9, 10, 11, 9, 10, 11, and for it the prediction will be what was that? 16, and so on. So this is how the dataset preparation for LSTMs is done. So this is what it is doing in create sequence. Now we are having the load and preprocess file. This is simply just transformation things to normalize the values of input and output. Then we have this normal loop, training loop. We are running over an epochs. We are just running loss. We have input some targets. Then we are just zero grading the optimizer. We are outputting the LSTMs. Then we are calculating the loss. We are converting the loss backward, appending the loss, and then saying to step up for the optimizer. These are pretty much it, and I think this other thing is just classical ML stuff. So we'll just quickly load it up. Let's run it for 100 epochs only. So the training has started and we can see the losses going now continuously. So let's just let it train. One more thing about the loss part is that we have this particular stuff over here when we are trying to predict it. Torch.nograd. So torch.nograd simply tells the LSTM that while this particular forward is going on, so at the core, what it is happening is the inputs are getting passed through LSTM, then through a fully connected, then final output is calculated over here by hat. Then it is getting compared to actual y, and then all the things are getting back propagated, and again it go forward with the updated weights. So when you're trying to inference with the model, inference is simply one forward pass through the entire model after all the training and the weight updation has been done. During that time, we don't want the model to compute the gradients, because model training has already happened and we don't want the weights to update after we have reached a certain step. So we'll just say which torch dot no grad, that is while this forward pass is being done, do not compute the gradients or back propagate it. So this is dos.nobladish. Um, so let's just wait for a few moments more. Yes, our model has streamed. We'll just simply normalize the test and then we'll just plot it out. So this is the blue one is the actual temperature and then red one is our predicted temperature. So it is not pretty good because it's just simple data and we have trained for 100 epochs. So if we train for more epochs, it will be giving us better results. So this is just a simple LSTM, its architecture and then how the flow is done. In the next slides and in the next video, we'll be starting with embeddings. Quick overview of embedding is that embeddings basically tells the essence of data to the ML, to model or whatever. So, for example, just an overview. So, what embedding actually does it, for example, if you have a word king, queen, and dog, let's say it is represent some let's say you apply certain transformation and represent into a vector of let's say three elements 1.0 1.1 and 1.5. So the king and queen comparatively, if you take king and queen model dot product of king dot queen, it should be somewhat, if let's say 0.4, then dot product of king with dog, it should be much more than what it was between king and queen, because king and queen are still similar objects when compared with king and dog. So these vectors are such generated such that a dot product whenever we are taking that represents certain essence of relation between each words or each sentences. So this is an overview of embedding and we'll see it in the next video. Different methods of embedding, which one are used and what are their inputs requirement. Probably a paper discussion about all those. So yeah, see you in the next video.